So hi, I'm Greg Maxwell, and I work on free codecs with Zip.org and Mozilla. The Zip.org part's pretty easy to explain, right? Zip.org is a nonprofit that was created for the purpose of building royalty-free codecs, and the tools associated with them, and doing education in that space as well, because sometimes to build something, you have to build the engineers to build it. Mozilla isn't just to the source of Firefox, right? Mozilla has a very broad remit related to building openness, innovation, and opportunity on the web. And as the web has started picking up more and more multimedia, problems in the openness and freedom of codec infrastructure has become a barrier to the web in general. So Zip.org doesn't have any employees. It's a nonprofit formed by open source hackers building interesting tools. And Zip.org people work elsewhere. These days, most of them work at Mozilla. So I'm part of a team that's been doing that. I've been working with Mozilla since January. I've been working with Zip.org since around 1999. I worked on Vorbis, on the improved Theora encoder, and I worked extensively on the Opus codec, which I'm going to talk about some today. So codecs are a kind of interesting thing, right? They're a very crisp set of problems. It's this little black box that is kind of all self-contained. It's very much like embedded system programming, where you do little small bits of code, and they're very intricate. You spend a lot of time per line of code, and you get great big results from doing them. Except, in embedded systems, you have these problems with this messy hardware with inadequate documentation and stuff that doesn't work the way it does, and you think it does, and it breaks, and it's just a mess. In codecs, we don't have that problem. Instead, we've got like really simple things to deal with, like human perception and patents and standards body politics, advanced mathematics. But it's a pretty interesting space. But importantly, it's an important space. Right. So I wanted to start off a little bit and talk a bit why I think that free codecs matter. So codecs are used by all multimedia software. They're the basic underlying infrastructure that the software needs to make it go. And every cost that a codec has ends up repeated a millionfold. You have codecs in every layer of the application, in every device. Your personal body is now carrying around with it like 3 or 4 AAC licenses. So as a result, codecs that come with licensing encumbrances are this enormous billion-dollar-a-year tax on all the communications infrastructure that we use and we build our world out of. And the licensing that these things are often placed under is used as a weapon in corporate competition. People go and get injunctions against importing devices into various countries. And they interfere with people that are even in places where the patenting regimes enabling this licensing don't exist. It's a problem for everyone everywhere in the world. Maybe a little problem at sometimes, but it's one that adds up to over and over again. Many of the existing standards that are not royalty-free are under these reasonable and non-discriminatory terms. But licensing regimes are universally discriminatory. The very nature of requiring licensing is inherently discriminatory against free software. And the business models behind licensing discriminate against all kinds of neat and new applications. If you have an application where it inherently requires giving away lots of copies of the decoder or display device, then licensing that's related to that is a problem. Many of the licensing schemes used today have nonlinearities where if you're a really big entity, you hit a cap. So even though you'd have the most means to go and build alternatives to this stuff, you're not incentivized to anymore because your marginal cost is 0, and all your little competition isn't, it has to pay licensing fees that you don't have to pay. So in particular, we can see when we look at historically networks that existed before, the telephone network and things like that, they were all very controlled, but the success of the internet was being able to innovate without asking for permission, right, or begging for forgiveness. In particular, in many applications where you're giving away zillions of copies of things, just the cost of counting who's using your software to comply with a licensing regime is just too great. And if you ignore the licensing, this is a tax, right, on success, because you're invisible, no one cares, and then you become popular and someone's looking for their settlement. This is all complicated by the fact that most of the time in many applications, what we really care about is compatibility. What codec do you want to use? Well, you want to use the codec that will actually work, that will talk from one device to another device. And so there's great big market forces that push people into using one codec or another. So this mess of incompatible codecs is a big problem for people, even when the licensing isn't a concern. So yeah, so you've got the guy that makes codecs saying, well, the way to solve this is that we need another codec. And I'd actually like it if that weren't the case, right? MP3 is coming off of patent now, basically as we speak. People are trying very hard to convince you that you need 22.pi audio and upgrade to the latest stuff of new 20-year patent terms. I'd much rather that we didn't need new codecs. But that compatibility point also means that those people who do need 22.pi audio and who do need quad ultra HD smell-o-vision, three-dimensional whatever, right? like I don't think most people need that, but those who need that are going to demand new codecs with higher performance. And then we're back into the compatibility problem of now you've got to support that too. In cases where a royalty-free format has really been firmly established, right? The canonical example would be JPEG. No one's pushing a non-free format. Like, there are proprietary image formats, Mr. Sid, right? But who's ever even heard of that? Once something's really become royalty-free, it's done, right? That decides it. People would prefer to stick with that. They'll even compromise on other concerns. But getting there's hard. People care about many things, right? Some people do care about the quad ultra HD smell-o-vision stuff. And so when you build a codec, it's not good enough to be just royalty-free, right? You've got to be better in every way that somebody would measure it. And so to do that, you have got to build codecs that are better by all of these different metrics in order to convince everyone to switch over and overcome the network effect. So the first codec I'm going to talk about today is Opus, which is a new audio codec that we've recently finished. It's a lossy audio codec, right, designed for the internet. So it's extremely flexible. And Opus was the product of a many-year work with major contributions from Ziff.org, Skype, which then became Microsoft, Broadcom, Mozilla, and many others. We did this in the IETF and published the work as RFC 6716 last year. So originally, audio codecs basically fell into two major classes: speech or communication codecs, which were for voice, and they were low delay, but they had limited quality, limited bandpass. And we had audio codecs like MP3 and Vorbis that were very high delay codecs. They weren't suitable for VoIP, but they had reasonably good quality or could reach it at sufficiently high bit rates. Now, the world has advanced, and we'd really like to be able to achieve both these things. There also were no existing high-quality, low-latency codecs. And when I mean low latency, I'm talking about below VoIP, stuff for like telepresence. So in 2010, if you were going to deploy codecs in a number of different environments, you'd need a collection that looked like this just to cover the spectrum of applications, right? You'd need things like AMR, narrowband, and wideband, or speaks in the VoIP use cases. You might use Vorbis for high bandwidth streaming. The low bit rate streaming, Vorbis was becoming a little bit old. Like, AAC has revved itself several times since it came out. We've got about 12 different versions of it. And it was being outperformed by high efficiency AAC for a very low bit rate, below 64 kilobit a second streaming. And there was basically nothing that you could use for efficient network music performance or real low latency telepresence. Right? Well, the idea with Opus was to change this, right? Get rid of the codec soup. Let's do it all. And so in order to do that, we basically needed to cover the spectrum from very low bit rates to very high bit rates, and to do it all with very low latency because of the applications that cared about latency. And achieving low latency is a little bit of a challenge, because in compression, you want to process lots of data at a time to compress it a fair way. So we ended up building something that was extremely flexible. They had this very wide spectrum of bit rates. It would work great with speech and music, mono, stereo, and multi-channel. And importantly, all of the stuff was switchable dynamically while the stream was running, and without having the user of the stream have to tear down their flow graph in order to do it. So I said Opus was optimized for the internet. And yeah, that means things like, okay, it has to deal with packet loss, sure. But really you can think of the internet. Remember I said like the internet was successful because you could innovate without asking for permission? Flip side of this, the internet is something of a war zone where the behavior of what users expect from applications and what the network will actually provide are often wildly inconsistent. So the network in one moment is a gigabit a second, the next moment it's cellular and it's dropping packets. The user is on a phone call one minute, the next minute they're trying to send music over their line. And so by being super flexible, even while the call is running, it enables to fit people's expectations of the kinds of things they can do over the internet. One of the other things we did with Opus that was sort of this product of experience in working on Vorbis and Speaks and other codecs was that we intentionally designed Opus to be hard to implement incorrectly. So that in Opus, instead of having this psychoacoustical model that analyzes the audio and decides how best to encode it and then signals its decisions, we structured the format to respect psychoacoustics to begin with. And so if you produce an encoder which produces a valid Opus stream, the quality will be pretty good, just due to the structure of it. That also saved a bunch of bits per packet and signaling all of that information, which was important for being able to do good low latency. So this was basically a product of taking two initial starting point codecs, Silk, which was Skype's speech codec that they created, and Kelt, which was a codec that we started at Zif.org in 2007 that was targeted at low delay audio. And we combined them not just with a great switch that flips between two different codecs in one package, but actually running them concurrently, mixing together parts of them. And so we could do things that neither of the two alone could do. And we took this, we developed it in public. We did massive scale. I ran a 160 core cluster during the whole development time. We ran hundreds of thousands of hours of audio through the system and automated testing. We deployed early versions of the codec out to users with Skype, millions of people. Early versions of the codec with open source Mumble software out to 1 million people or so, and got real-time feedback on how the codec was working. And we got some really good results out of it. So there's been a bunch of testing, and I've just sort of selected out a couple of examples here. Here's some testing Google did on speech, and we can see Opus at, I think I have a pointer. Oh, I don't have a pointer. Oh, yes, I do. We can see Opus at 20 kilobits a second, easily outperforming things like G719 at 32, AMR wideband at 20 kilobits a second, right? And Opus at 32 kilobits a second, and this is for speech, is very, very close to the original audio in this listening test. On music, we also have excellent performance. This is a test done by Hydrogen Audio, which is a very scientifically minded internet forum that did a massive listening test with just hundreds of hours of listening. And it compared Opus, two different HEAC encoders in Vorbis. And the chart at the bottom is basically showing where the green lights are where Opus was better than all of the competing codecs in the test. And so pretty consistent across the board, superior performance in a couple of samples where Opus wasn't as good, but overall the performance of Opus was much higher than the other codecs. So with Opus we have something which is basically the current state of the art in almost all audio applications. It's royalty-free, but that doesn't mean unpatented. We actually went out and applied for patents, which enabled us to negotiate with parties like Broadcom and get them to enter into the exact same patent licensing terms that we used. And the patent licensing terms we adopted were ones that basically permit all uses, all applications, so long as you don't sue anyone else who has a valid Opus patent license for using Opus. And if you do, you lose your patent license, and everyone else that has Opus patents can sue you. So it's a disarmament patent license. With the fact that our implementation has a good high-performance fixed and floating point implementation. We're able to get Opus into lots of places very fast. And so, today you can use Opus on little devices like Rockbox portable music players. It's been deployed to hundreds of millions of computers in web browsers. And mind you, this is a standard only finished about a year ago. And it is now mandatory to implement in the WebRTC specification. It doesn't end there. We're continuing to improve Opus. There's work going on to improve the encoder, right? The bitstream is frozen, but we're improving the encoder. And we've done things like improve performance, and the little red boxes in this chart now are green if we were to do this test again. We've fixed those cases. So it's been a pretty tremendous success. So that's audio, and audio is kind of boring because networks are fast now. Let's just all send lossless. Lossless video is still well over a gigabit a second. So what about video? So there are existing royalty-free video formats, things like Theora. But Theora is technology circa 1999-2000, and we did some amazing stuff with the encoder to really improve the performance, but there's only so far that you can get by putting rockets on a pig. VP8, when it came out, very good performance compared to H.264 baseline profile. High profile, more mixed, and people are successfully deploying that now. VP9 has sort of turned the crank and advanced that forward. But what I've been seeing a lot of is that it's very easy to FUD the design of VP8 and VP9 because they use a design which is very structurally similar to existing patented technology. Regardless of whether or not any arguments are valid, it makes good FUD material. And some parties are really uncomfortable with a standard developed by a single company, particularly when it is the 900-pound gorilla of Google. There's been some work in MPEG on royalty-free formats. MPEG has this very distorted model, and it's really not managed to get its act together on it. There was a lot of talk about building a format that would basically be an enhanced version of MPEG-2 with performance maybe basically comparable to H.264 baseline, and that's not particularly exciting to anybody. There's now work in MPEG to effectively rubber stamp VP8, and I suspect most people that want to use VP8 are already using it. A few parties that care about formal standardization might mind that. So what if we could take some of the good things that we did with Opus and apply it to working on video, right? Build a new codec in a standards body that doesn't have people pay to join it, which uses a public process with a strong IPR disclosure policy. What the IETF requires isn't that you agree to some ambiguous RAND terms, but when you assert patent information on a work at the IETF, you actually have to disclose your patent numbers, which provides a tremendous opportunity for the working group's participants on their own to go and analyze, do these claims make sense? Are they invalid? Can we work around them? Can we negotiate licensing? Whatever, while the codec is being worked on. And can we do this while basically throwing out anything that needs to be thrown out in the conventional structure of video codecs? Right? What we've seen in the development of codecs like VP8 and H.264 is they've really continued on the same design history that started with JPEG and made incremental improvements. And we do something different that both breaks some of the patent minefield in the area and allows us to get some improvements in performance. And we should do this while optimizing for perception and not dumb metrics like PSNR. And this sounds obvious, but in the royalty-bearing world, the parties participating in that need to fight to get their patents into the standards so that they can cross-license with each other and not pay royalties, and so that they can receive income. And so what you see in a lot of royalty-bearing standards is things like using PSNR to break ties on what goes into a format. And it's a terrible metric. So Daala is the name of the project that we're working on to advance these ends. And we're doing a couple of interesting things technologically in it, and I'll talk about some of these things. But before I go deep into codec internals, I thought I would give the 30-second intro to compression so that maybe I reduce the number of people totally lost by a couple %. So the general structure of a lossy codec, be it for audio, video, whatever, is that you start off, as you're coding a frame, as you're moving through it, storing data about it in the bit stream, you predict what the upcoming data is going to be based on the past data. Right? Maybe you predict that it's just going to be the same thing as the past data. You potentially transform the data that you're about to encode. It's represented one way, and you represent it a different way, the same data, in a way that makes it easier to compress. So the example I'm showing over here is the discrete cosine transformation. And this says instead of representing a block of pixels as a bunch of pixels, we're going to represent it as these smooth functions. And the reason for doing that is because typical images are full of areas that are just smooth. And so if you represent image data as a sum of smooth functions, you end up needing not too many values in your summation. Doing that is where most of the compression in JPEG comes from. Once you've got your transform predicted data, you have some error from your original, right? How is this prediction transform stuff wrong? And you quantize it, throw away data, because we're lossy here. We're going to lower its precision. And that leaves you with a series of numbers that come out, and hopefully they're small, because you predicted things well, and you transform them to a place where they compress well. And now you've got all of these small numbers that have some probability distribution, right? Most likely small, maybe mostly 0. And so then you do entropy coding, which is just the process of taking numbers under some probability distribution and efficiently packing it into a bit stream. So the typical way that state-of-the-art video codecs have done this entropy coding portion is using arithmetic coding. And arithmetic coding normally is referring to the binary version of it, where you have symbols that come in that are ones and zeros, and they have some probability, and then you encode them efficiently into the bit stream. There are the fast approximations that you can do to make arithmetic coding fast, but many of them are patented. And arithmetic coding is inherently serial. So this is a problem, particularly for hardware implementations, where your clock rate ends up getting determined by running your arithmetic coder. So in Opus, we used a variation of arithmetic coding called range coding, which basically says your symbols aren't just 1 and 0, they're a range of many possible values that you have some probability over. Doing so has a number of patent-related improvements. It also allows us to do some extra things for video. It turns out that when you use a multi-symbol coder that's coding multiple possible values, it reduces the serial portion of the coding process, because handling the probability updates on a range of multiple possible values is inherently parallel. And so just doing this and taking VP8 and replacing the arithmetic coder in it with one that uses this multi-symbol stuff give an immediate 2x speed up. One of the biggest points of departure that we're doing in Daala is this concept of lap transforms. So a major video coding artifact you get with traditional codecs is this blocking behavior. In video codecs, to avoid blocking, use these post filters on the images that distort the images more by blurring over the blocking boundaries, throwing away more information. So the idea here is that we can apply a matched pre-filter before we code the image that basically blocks the image up. And then on the other side, apply a matched post filter that removes the blocking again. The end result of this is effectively getting rid of just these fixed blocks in our format and instead having overlapping blocks in the images. This completely eliminates blocking artifacts without needing this information destroying filter at the end. There's some other techniques that go and remove blocking artifacts by wavelets, but they don't necessarily look particularly good perceptually, and they can be computationally expensive. This lap transform stuff is computationally cheaper. And it does work with data that's in blocks, even though the blocks overlap. So it doesn't totally disrupt the whole structure that you would build a codec out of. So instead of those smooth basis functions I had a few slides up, we now have these blurry smooth basis functions that have these overlapping edges. So in a typical video codec, we use intra-prediction, which is this notion of predicting a block from its already decoded neighbors, right? So there's a block in the center that's being predicted, and there's the surrounding decoded pixels, and we just extend those through in some directional mode. So this is a pretty flexible mechanism, does a good job for prediction, and you can make it work with any number of angles that you want to predict images through. And it's computationally efficient. There's few or no multiplies in implementing it. The problem with it is, for us, is that it doesn't work with overlap blocks, because in order to predict from the surrounding decoded neighbors, you have to have the surrounding decoding neighbors, and our blocks are overlapping. So we can't decode those blocks until we're a little bit away from them. So in this case, we're decoding this brown block in the center, and then there is the surrounding blocks that we can predict from. And then this gridded area around them, we can't actually predict from because that's overlap, the brown block in the center. So we took a look at this and said, well, we're going to need something like interprediction to get the performance we need. But we need something that will work with our overlap blocks. And so instead of doing the prediction in the pixel domain, we decided to try doing prediction in the coefficient domain. And if there weren't any overlapping in this case, you could construct the same predictors in either domain, because that transformation could be applied just to the prediction. But in our lap domain, directions don't really have any clear meaning. So how do we construct these predictors of our transform coefficients? So what we've employed to do that is machine learning, where we actually go through and use like the VP8 classification of blocks into directional modes, and then use that to assign each of the blocks in the image to a different direction, up, left, down, whatever the modes were. And then we're able to just run a linear regression to design multipliers to read from our predictor coefficients to predict our pixel blocks. So for a 16 by 16 block, we end up doing a simple linear regression with 262,000 dimensions. There's a little extra work we have to do to then reduce the multiplies, because doing 262,000 multiplies per pixel isn't really good. The result we've gotten is that with bringing that down to 4 multiplies per pixel, we're able to get significantly better performance than the pixel domain predictors while having something that works in our lap transform domain. One of the other side effects of this is that we're not just stuck with getting predictors that work on directions. So a rose on its own out of the machine learning process is that we ended up with one of our modes actually predicting periodically repeated textures. You can see in the top of the image this sort of grid pattern. And we have one of the modes naturally arose to predict that well. One of the other ideas that we're using right now in Daala is pyramid vector quantization. And this was a technique that we used in Opus to tremendously great effect. We discovered while developing Vorbis that it was very important to get the energy in each audio band correct, even if the details were wrong. Right? If there was noise there, you needed to have noise at the right volume. It didn't have to be the right noise, but it had to be at the right volume. And so in Opus, we designed an encoding scheme that basically codes the energy separately from the details. And then we can be assured that we always preserve the energy, even when our bit rate is low and we're not keeping the details. Intuitively, this makes sense for video as well. Right? If we lower the quality of a section of video, we don't want that to get blurry, right? We may want to preserve how textured or how edgy or how noisy that is, like film grain, but not use a lot of bits on it. So we have this implemented, and the results so far are kind of mixed. The objective metrics like PSNR, of course, hate it, as expected. Visual comparisons of it, it produces very different artifacts than other techniques, and it's not clear if it's actually better yet. So we're continuing to refine this set of ideas to see if it'll actually work out. We've been doing a technique called chroma from luma, and it seems like an obvious idea, which is that the conversion from red, green, and blue to YUV decorrelates the channels, moves most of the information into the luma plane. But there's local correlation, right? If there's an edge in the luma plane, there's usually an edge in the corresponding chroma planes. with all this prediction we're doing in the transform domain, there's a fast way that we can predict the chroma planes from the luma plane. And this is something else that the objective metrics like PSNR hate, but it actually looks better in subjective testing. One of the biggest parts in a video codec is motion compensation. So you want to predict the current frame from prior or future frames with adjustments for things moving in the images, because we know in video things move. But the traditional way of doing motion compensation works by just taking blocks of pixels and displacing them. Doing this would create blocking artifacts, and we just carefully avoided creating blocking artifacts with our transforms. It'd be terrible to create them with the motion compensation. There's also a ton of patents in the motion compensation space, so doing something different in motion compensation can be helpful. So what we're using is overlapping block motion compensation, which is something that the Dirac wavelet codec also used. Just the idea that you have blocks, but they have overlapping edges, and so a set of pixels will have contributions from its neighboring blocks. You can also look at it as a form of multi-hypothesis prediction, right? Like, this pixel may be over here or maybe over there. Let's take these two hypotheses and blend them together. So this actually can have some pretty big improvements, but it can also produce some issues of its own. It can add blurring because we're now blending together values, and so edges that were sharp before may become smoother. Although with our pyramid vector quantization that preserves energy, that's less of an issue. It can also add ghosting, where two motion vectors are disjoint, and there may be a line or a feature in one and not in the other that may bleed through and be visible. And it's tricky implementation-wise to handle multiple block sizes. So we needed a way to change block sizes so we'd have different regions of motion without itself creating blocking artifacts. Dirac solves this by basically using the smallest overlap everywhere and then just copying the values down, which works, but it doesn't allow you to get the advantage of a larger blending area. So we came up with a scheme to do dynamic subdivision that works inside our OBMC. And the basic idea is that you start off with the biggest block, and then you can recursively subdivide it down by adding a single motion vector in the center, and then adding the motion vectors around the edges, and then the one in the center. And this allows us to subdivide it down. We're also doing this fancy optimization that deals with the fact that now these motion vectors are no longer independent. And a lot of this is work that was developed for computer vision and for other areas that we've been able to apply to video coding. One of the other things that we've been trying out is multi-resolution blending. So this is basically the same idea that's used in the InBlend panorama drawing tool, panorama rendering tool. And the idea is that you take the image that you're going to blend together and you separate it out into low-frequency parts, the smooth parts, and edges, the high-frequency parts. You blend the low-frequency parts with the big, large, smooth window, and you pass through the high-frequency parts. You don't blend them together. And actually, in doing this, we're able to improve the performance of the result and require fewer multiplies. So another thing that we've been thinking about but haven't tried out yet is the notion of using edge-directed subpel interpolation. So when you're predicting motion in video, sometimes the motion isn't just an integer number of pixels off, right? You'd want to go halfway between 2 pixels or a quarter way between 2 pixels. And so you need some way to interpolate what value is existing at that, in that intermediate step. So normally what things do is this linear filters, right? And they'll use something like a 6-tap linear filter that smoothly interpolates between the values. And what this ends up doing is blurring the image. And blurring the image is not the worst thing you could do. It's certainly better than just not having subpel and repeating the values. But it means that the prediction over time becomes blurrier. And one of the things that we can recognize is that we know something about how images are structured, and we can do something better than just using a linear filter. We could start out with this prior hypothesis that says that edges tend to be continued. Instead of just applying this blurring filter, we can apply a filter that continues edges in the image. And there's been a ton of research on creating image interpolations that produce more accurate images, with that assumption in mind. But most of them are not fast enough to use inside a video codec. David Schlief has built something that should be fast enough, but we haven't had a chance to try it out yet. So there's a bunch of techniques that I've talked about here, and they're the things that we've got implemented so far and appear to be working pretty well. There's a lot more that can be done. Like the area of video formats is far from exhausted. We basically just need more time and engineering to make a lot of extra ideas possible, and of course Moore's law to keep making computers faster. And just to give you an idea of the sort of things that are sort of mind-blowingly possible, is a common problem in video coding is that you're coding from a reference that's two images that have been blended together during a crossfade, because that's where your iframe fell in the sequence. And then you end up spending a ton of bits coding out the difference between this blurry, blended together image and the image you're ending up with. It's actually possible, from a signaling processing perspective, to take this blended image that's in the center here, where you can see the two things sort of ghosting together, and actually reconstruct out of it the contributing images. And this is possible because we can say that both the contributing images were smooth. They both would have had sparse DCT representations. And so as the image is decoded, we can take the error that came out and say, well, what would be the smooth continuation of that error? And what would be the smooth continuation of the image we coded? And by doing that, actually separate out from the image. These are real images created from a real technique. These are the actual outputs. And this particular implementation is just some very low performance academic piece of code, not optimized at all. And it runs at about a frame every 2 seconds. With some optimization, some neat things are possible. So right now we're trying to get more people to participate in this work. The industry in general is very distracted right now with HEVC or VP9, getting that actually out and deployed, even though they have no idea when it's going to have licensing available. We've had some interest from Google and from Cisco in participating more in this. But we're generally looking for more people out in the open world to participate in this stuff. I'm very interested in hearing from people about what applications are not well served by video codecs today. Opus had tremendous gains from the fact that it did this low latency stuff that basically nothing else did. I don't know if something like that exists for video, but if it exists, I'd like to serve it. So, questions?
Hi. Is there do you have a goal for Daala? When
I do, and I didn't mention it because I'm a terrible speaker. Yeah, so we're targeting to be a next generation format beyond where VP9 and HEVC are. And we're looking at doing that on a time frame in the standardizations process in 2015. So we have a little room on there. But it took a long time to do Opus as well.
Where are you today?
We are not as good as VP8 today. But that's not surprising. We haven't completely integrated all the stuff that we've been playing with. So we've basically been trying out all of these parts and measuring that they work well in isolation. We have them kind of integrated. There's a lot of basic engineering work that needs to be done to get the performance competitive.
Which companies currently contribute to Daala development?
So we've had contributions from, of course, Mozilla and some stuff from Cisco people. I think what we found with Opus is that nobody cared about Opus until the codec was basically being a pants off of everything else. And then everyone suddenly was very interested in it, and the IETF working group started to write up, and we got lots of contributions. I'd like to not have that happen again. I'd like to have more contributions from more people earlier on, but I don't know if it'll happen.
Do any of the people currently working on Daala, or are any of the people working on Daala involved with any people who work on hardware decoders and encoders to ensure that it's
Not
implementable
yet.
for embedded? Because obviously that's going to be a very big market.
Right,
That
so
needs to be satisfied.
we have indirect experience from working on a bunch of other codecs, but we definitely need and want and intend to obtain more people with direct hardware experience.
Do you know of other implementations of the Opus codec other than the one that ZIF provides?
So there is basically two that I'm aware of, incomplete implementations. There was one that was done as a Google Summer of Code project as part of FFmpeg. And there's another implementation that was done by one of the other ZIF people, one of the other Opus authors, did a separate implementation that we used for validation of the format. And that one's almost completely complete.
Regarding Opus, what improvements do you see coming for next versions, like improved concealment and stuff like that?
So we made some concealment improvements already in the 1.1 Git code that's not published yet. It basically fixed a couple of buggy cases in the concealment. It sounds a lot better now. It's not a real big fundamental change. So for 1.1, I don't think that we currently have any more concealment improvement plans. It's mostly right now more performance improvements, ARM assembly code. We made a bunch of perceptual improvements, improved analysis in the encoder. And I think that we'll see more of that going forward into the future, improvements under loss conditions and improved encoder analysis and more performance tuning.
Right now we have H.264. From looking to the future, when you will be, or for the time you want to be ready with your Daala video codec, do you know what the competitors are or will be at that time, or do you have an idea what else is going on that side?
I mean, clearly HEVC will be a competitor at that point in time, and we'll see how that pans out.
That's the only one.
That's all that I'm aware of. And so, yes, VP9, and I really don't expect our Daala work to compete with VP9. If we're successful with the project, I would expect our Daala work to be basically filling the VP10 role. And we've heard positive sounds from Google along those lines as well. Said Google's interested in our work.
If you aim for 2015, are you not afraid you might be too late? Because by then, basically the entire industry might have sort of already rolled out HEVC, and that's sort of the new next iteration, and then you come 1 or 2 years later.
That's why we have to have performance better than HEVC.
But do you intend like some kind of gradual rollout, and then you stabilize in the spec, but
so
everyone starts
we will certainly have pre-final rollout in some applications where that actually makes sense. Where you're not encoding to files. That was a big success for us in Opus. Video, there may not be as much potential for that, but we'll see how that works.
So Opus got into being a mandatory codec for WebRTC.
Yes.
Was that mostly because of the latency capabilities of it that made it a compelling option, plus it fulfills all the other roles of all the other different types of audio codecs?
So we were developing Opus basically at the same time WebRTC was going on. And WebRTC had this long list of applications that had to be covered in different use cases. So we made sure Opus covered all of them. So So Opus is a very good fit for it. And the decision to make Opus mandatory to implement in WebRTC was very strong in the IETF. It's close to a unanimous decision as you ever see in the IETF.
So Opus was a very clear choice to become part of a popular web standard that's now going to be deployed widely on the web. So obviously it drives the uptake of Opus.
Correct.
Is there anything like that for Daala?
Not yet, but 2015 is still a ways out.
Yeah.
Just a comment, I mean, based on what Tim said as well, I think availability before 2015, similar to what you did with Opus, making it available in some use cases. So that's a metric-driven development where you get feedback as to how well it's working. I think is something that we probably should look at Daala as well from that perspective. I think it's probably more complicated. I understand that.
Yes, and I absolutely am very interested in talking to people who want to participate in doing that. I mean, it worked out well for Opus because Mumble basically beat down our door. We need a low latency codec with better audio quality than Speaks. And it also worked great having Skype working on it, who had a captive audience of people to shove the codec onto in a software that secretly updates itself in the background.
Yeah. Should talk to Cisco.
Yeah.
Do you want to play us any sample video before you?
I can play videos. I don't have any really good sample videos of the codec output because it looks like video. Like I can show you things like the motion compensation that we're doing with the overlapping blocks, and you can see motion vectors. I can show you our interprediction that nicely predicts different directions. You can see different directional modes. I don't have any good demonstrations right now of the image quality, and one of the reasons I didn't set them up is I've had terrible experience in the past trying to show images on projectors in rooms. This one's better than most. I probably should have. But usually I'll show some images and people go, oh, well, that's an image, and I can't see the difference between the two of them. Yeah. Yeah.
Any more questions?
For video and your edge reconstitution work, do you find that for video people are more accepting of blurry edges just because that's how video are usually collected?
It is a cultural thing, and there are populations of people that are very intolerant of blurry artifacts and very tolerant of ringy artifacts, just sort of the opposite artifact that you get. That's why I said our PVQ stuff has sort of mixed perceptual results because we replaced the blurry artifacts with noisy artifacts, and it's different, and I think that we're not quite sure if it's better yet. Does it matter more? I mean, well, I mean, if you're talking about what people are looking at and used to, the stuff that's being distributed over cable TV looks horrific. I don't think anyone can really get used to that. I hope to do better than that. Okay, thank you.